Hey, what's up, guys? Yeah. So in order to like prove the so this video that I want to talk about the reciprocity law of this of the quadratic reciprocity. And before I will separate two videos. The first video that we will first prove this Eisenstein's lemma. Okay, so let me just quickly write down the strategy. So our goal is to prove this quadratic reciprocity in the next video. So let me just write down the idea. Okay, so the theorem which says that like for PQ which is distinct and odd prime, and we must have PQ Legendre symbol, QP Legendre symbol times will be -1, P -1, Q -1 divided by 4. Okay, so this theorem is very deep that can trace back to Gauss, and there are many other kind of like 200 proofs. Okay, and okay, so the first proof that I will give is this Eisenstein's proof. Use Eisenstein's lemma. So this video is proof Eisenstein's lemma. Okay. Okay, so the idea is Eisenstein lemma. So this lemma is similar to Gauss lemma. There's an idea that one can actually prove this by Gauss lemma. So I will like leave in the like a future video. Okay, so the idea the Gauss this Eisenstein lemma looks like this way. So you take even, let's say you take even integer from 1 to like u from 1 to p minus 1. And right, and I can take qu divided by p, right? I can do this and then write as floor function plus pru. So ru is a positive residue. Or simply speaking, ru is like, yeah, so basically ru is just simply speaking, ru is the first, or you just keep multiply u. So keep multiply the multiple of u, and until that the residue is until it's greater than p, and ru is a residue. Okay, so it should be, let me just write down the list. Positive residue of qu mod p. Okay, let's say we take for one example. For example, I take p to be 11, q to be 7. And for example, let's consider, so I can consider u, right? I can consider u to be, so in this case, u can be like even, right? Even number, so it's 2, 4, 6, 8, 10. And we can have our u. So 2 is less than, 2 is less than 2 is less than p, right? Right, q is less than p. So I want to take qu, right? So just 7 times 2 is 14, right? So it's 14 mod 11, so it's 3. And then we have 7 times 4 is 28, so 28 divided by 11, the mod is 6. Yeah, and the 6 times 7 is 42. There's 42 mod 11 is what? Is 9. And the 8 times 7 is 56, so it's 1. And 10 times 7 is 70, so it's 70 is 4. Okay. Okay, and okay, and we define a number, right? So we define a number -1 ru. Okay, so basically it's very simple, right? So you just take, basically what I'm saying, just take qu divided by p, and then take the integer part, and ru divided by p, right? So ru divided by p is always like less than 1. Okay, and okay, so we can see the following, right? So we want to say something. We want to say that what? We want to say that okay. So okay, so let me just, so this is mod p, okay, mod p. So what we want to say is the following, right? We can consider this number which called -1 are RU and R -1 to RU power times RU. And okay, so okay, so first we notice one the first fact. The fact is that they're all distinct, right? Because -1 R RU times RU is -1 like RV V and RV. Okay. And obviously that right, so you can easily show the following, right? So this will show that what? Okay, so this will show that since R of U is just some mod P, right? So if they are the same, that means that U is like at least a plus or minus T, right? Mod P. But this is impossible since we consider all this U from here. Okay. And yeah, so right, because we consider it's all positive, right? So right, so U must be so this cannot happen, right? So U equals to mod P. If U is T mod P, then both are even and P is odd, right? So okay, so this will force this, right? So this must be the same in mod P, right? But just unique. Okay, so I think one fact that need to be think a little bit is the following. Okay, so what I want to say is that -1 RU, right, is what? Is even. Okay, this is weird. So let's see, right? We have RU, right? In this example, we have 3, 6, 9, 1, 4, right? We calculate -1 RU, right? We get this is like -3 and the 6 and the -9 and the -1 and 4. Okay, so if we do in the mod P, that P is 11. Sorry, P is 11, right? So this is 8 and the 6 and the 2 and the 10 and the 4. Okay, the reason is the following, right? Because obviously, right, if RU is odd, then you times this become sorry, when RU is odd, right? You add a minus sign, right? And then you since P is odd, so it become even. And if RU is already even, then it's still even. Okay. So now we have this. Okay. But we showed -1 RU are distinct. Okay. And so number of -1 RU will be the even number from 1 to P minus 1. Okay. So the number of it total has P minus 1 divided by 2 even. Okay. And then since they are all distinct, so a set of these must be the permutation of 2, 4, 6 up to P minus 1. Okay. So it must be the permutation of 2, 4, 6 up to P minus 1. Okay, so now I can consider the following results. I can consider the following products. I can consider -1 R of 2, the 2Q, and the -1 R4 for Q, and up to -1 R of P minus 1, P minus 1Q. Okay, so notice that right, as I said, right, I can when I times Q, then I just shift 2, 4, 6, right? Another permutation, and I get -1 R of 2. It's basically just the same thing. Okay. So this will just be the permutation of 2, 4, 6 of the P minus 1. Okay, so it will just be the permutation of 2, 4, 6 of the P minus 1. Okay, in the mod P. Okay, since P is odd, so I can cancel this 2, 4, 6. Okay, so finally I will get the following. that I will get the Q P minus 1 divided by 2, right? Because I get this equals to minus 1, right? So I get 1 R2, R4. There will be additional minus sign, right? But since we only care about Ma2, so it's fine. So we get R4 out to RP minus 1. Ma B. Okay. Okay. So from the previous results that I write QUP equals to QUP this plus RUP. So this will imply that QU equals to P QUP plus RU. Okay, and notice that P is odd. P is odd. Okay, so that means what? That means that this guy is an integer, right? This guy is an integer. And this guy is another integer, right? So this implies that QUP and RU are the same. Ma2. Okay, the why? Okay. So because this is even, right? This is odd. So this guy must be like even. Okay. And the P is odd. Right. So if R of U is even, then this guy must be even. If R of U is odd, then this guy must be odd. So that their added can be even. Okay. So it must be Ma2. Okay, so this gives me like really weird results, right? This proves that Q of P minus 1 divided by 2 is what? It's just summation, it's just minus 1 of RU, right? Sum of RU, right? Sum of RU. It will just be sum of RU. And what is sum of RU? Sum of RU just P Q, just Q divided by P, right? Because they are the same Ma2. So we can just QU divided by P at least. And our so U. Okay. So U is all the odd even number that from 0 to from 1 to P minus 1. Mod P. Okay, so this guy is also just by definition is just QP Legendre Symbol. Okay, so this is what I want to show, which is this Eisenstein lemma, which basically this QP is just minus 1 U QUP. Okay, so you take this, just try to compute these results. Okay, and okay, okay. I think once we have this in the next video that we can prove the Legendre reciprocal this reciprocal law. Okay, see you guys next videos.